earlier I said that the product of inertia arises when you try to write transformation equations, which you can use to rotate moments of inertia in a coordinate system at some angle from your original XY coordinate system. And so when you write those transformation equations, an IXY shows up in the derivation. And so the IXY value, or the product of inertia value, plays a role in finding moments of inertia about rotated axes, which includes the Imax and the Imin at whatever orientation they occur. And ultimately, the Imax and Imin are fairly important values that we want to find. And so IXY is a key piece in doing that calculation. So this is a derivation of the transformation equations. It's a little bit complicated, but it's fairly important for you to understand. We're doing it now for area moments of inertia to get to these transformation equations, and then we're going to set up Mohr circle based on these guys. So for now, we're doing it in statics for area moments of inertia. But when you get to mechanics materials, you're going to do similar transformations of normal stress and also transformations of strain. And it all follows this very similar derivation. The equations are kind of similar. The Mohr circle is kind of similar. So don't think this is a one-off deal. Don't think this is just a weird niche topic that you're never going to see again. What we do here is laying a foundation for what you're going to do in mechanics materials. So you're not going to learn it super well, but I want you to learn it well enough that you get the hang of it, and you're better prepared to go on to be successful in mechanics materials. So this is the problem. We have an area in an XY coordinate system. There's a dA here. We're going to assume that we know Ix, Iy, and product of inertia Ixy for this area in this coordinate system. We're going to define an R distance from the origin to the dA. We're going to define an angle alpha and a distance x, which is equal to R cosine alpha, and a distance y that's equal to R sine alpha. Next, what we're going to do is we're going to draw a set of rotated axes. So this set of rotated axes are rotated at an angle theta from original x-axis. We still have the same R distance, and we're going to call this a x prime, and we're going to call this a y prime distance. And our goal is to find a moment of inertia of this same area about this x prime axis, about this y prime axis, and a product of inertia I x prime y prime about this rotated set of axes. The angle from this R back to the x prime is equal to alpha minus theta. Thus, x prime is equal to R times the cosine of alpha minus theta. The y prime, again measured in this rotated system, is equal to R times the sine of alpha minus theta, which makes sense. So this is an x prime and a y prime. Once we define those, then we can use difference angle identities. And so x prime is R cosine alpha minus theta. But using a trig identity, that's equal to R times cosine alpha, cosine theta, plus sine alpha, sine theta. And y prime, which is R sine alpha minus theta, using a trig identity, that's equal to R times sine alpha, cosine theta, minus cosine alpha sine theta. But we're going to sub in x is equal to r cosine alpha and y is equal to r sine alpha. And so if you look up here, there's an r cosine alpha. Well, that's x. There's an r sine alpha. Well, that's y. There's a r sine alpha here. That's y. And there's a minus r cosine alpha. That's x. And so these guys simplify to x prime is equal to x cosine theta plus y sine theta. And then y prime is y cosine theta minus x sine theta. So if we've simplified our definitions of x prime and y prime, which again are our distances from the x prime axis to my dA, that's y prime. And then the x prime is the distance for the y prime axis to that guy. So once I get those x primes and y primes, I can calculate the moment of inertia about the x prime axis. And so Ix prime is equal to the integral over the area of y prime squared dA. But y prime, we said, was y cosine theta minus x sine theta. And then we're going to square that times dA. When you expand this guy, you get y squared cosine squared alpha. Your third term is a positive x squared sine squared theta. And then the middle term is a negative 2xy sine theta cosine theta. If you multiply dA through all of these terms, then you have and remember theta is constant, theta is given. So the theta terms can come out of the integrals. So this first term is a cosine squared theta times the integral over the area of y squared dA. But that's Ix. This last term, we factor out a sine squared. This is the integral of x squared dA, but that's Iy. And finally, the middle term, you can factor out a 2 sine theta cosine theta, and you're left with an xy, the integral of xy dA, but that's Ixy. So literally what we have found is that if you have an Ix, an Iy, and an Ixy about an original xy axis, and you propose to find I about an axis that's or I about a coordinate system that's rotated some theta from x, then I about that rotated axis is equal to Ix cosine squared theta plus Iy sine squared theta minus 2 Ixy sine theta cosine theta. Wow. So this is a transformation equation. This takes an original Ix, Iy, and Ixy and lets me calculate a rotated I. For Iy prime, which is 90 degrees from Ix prime, it's equal to x prime squared dA. X prime is equal to this guy. You square him, evaluate the terms, and you get an Iy prime, which is equal to Ix sine squared theta plus Iy cosine squared theta plus 2xy sine theta cosine theta. Finally, for the product of inertia in that rotated system, Ix prime y prime is equal to the integral over the area of x prime y prime dA. Well, this is x prime, this is y prime. If you multiply those up, you get 4 terms. You get an xy cosine squared theta. You get a minus xy sine squared theta. You get a minus x squared sine theta cosine theta plus a y squared sine theta cosine theta all times dA. If you gather these terms together, you get an Ixy So wherever you have an xy dA, that's IXY. And so you have an xy dA by times a cosine squared, and then minus a sine squared. And so that's IXY cosine squared theta minus sine squared theta. And then you have an x squared dA, which is IY minus IY. And then you have a y squared dA, which is a positive IX. And so these last two terms are a positive IX minus an IY times sine theta cosine theta. So now we have three equations. We have an IX prime, an IY prime, and an IX prime, Y prime for those guys in a rotated coordinate system. I call these three equations the theta form of the transformation equations because they're in terms of theta. If you actually add equations 1 and 2 together, you get IX cosine squared plus sine squared plus IY times sine squared plus cosine squared, a minus 2IX sine theta cosine theta plus a positive 2IXY sine theta cosine theta. So these guys cancel one another. The sine squared plus cosine squared is 1. And so adding these two equations, what you get is IX plus IY is equal to IX prime plus IY prime, which is equal to I min plus I max, which is equal to IU plus IV, where IU and IV are just basically two I's at 90 degrees from one another. They're basically the same thing as IX prime, Y prime, but sometimes I use IU, IV for those. And this is called an invariant property, which basically says in my original orientation, my IX plus my IY, that's equal to the sum of my IU plus IV, or my IX prime plus my IY prime. And so it can be useful for you to find something, to find something from one of them from something else. The other thing that's interesting is if you divide all of these guys by 2, then you basically get an I average. So an I average is equal to IX plus IY over 2. So all of these combinations of I share the same I average. And what you're going to learn when we get to Mohr circle is that the center of Mohr circle is I average. And so you'll see that there. So these are the theta forms of the equations. So you can actually develop another set of transformation equations, which are basically the same equations, by using these double angle trig identities to replace the theta versions with 2 theta versions. And so if you start with the IX prime equation, which is cosine squared, sine theta, cosine theta, you can replace the cosine squared with 1 plus cosine 2 theta over 2, the sine squared with 1 minus cosine 2 theta over 2, and then the 2 sine theta, cosine theta, you can replace with sine of 2 theta. And if you gather like terms, you end up with an IX plus an IY over 2, which is I average, plus an IX minus IY over 2 times cosine 2 theta, and then minus an IXY sine of 2 theta. And so this is the same equation. We've just written it differently because we did a trig substitution. But this form is written in terms of 2 theta. And so I call this the 2 theta form of the equation. When push comes to shove, it's actually a little bit easier using the 2 theta form of the equation than the other. We'll do both here at some point. But again, notice that this 2 theta form of the equation has an I average as part of the equation, which is interesting. If we take the IY prime equation and substitute in the double angle formulas, we basically end up with an IY prime equation, which is equal to I average minus this term, and then plus this IXY term. And then if we plug the identities into the product of inertia, I, x prime, y prime, we get this form of the equation for the product of inertia. Again, these are all 2 theta forms of the transformation equations. If we add equations 4 and 5, all of these the second and third terms cancel one another out, and you're left with ix prime plus iy prime is equal to the average plus the average, which is basically ix plus iy, which is what you got earlier. So that's the invariant property. At some orientation, there's going to be, so if you have an I, U, and a V that vary at some angle, at some orientation, at some theta, there's going to be an I max and an I min. The question is, what are those I max and I min, and at what angle do they occur? Well, how do you get the theta p equation? If you start with an ix prime equation, take its derivative and set it to 0, that will give you the angle at which the max and min occur. So if you take the derivative of this guy, the first term is 0. The second term is minus 2 sine theta times this guy. The third term is a minus IXY 2 cosine 2 theta. If we set that equal to 0, we can solve for tangent of 2 theta p. And this isn't right. This is minus 2 sine of 2 theta. That's a sine of 2 theta. And so then we can solve for a tangent of 2 theta p is negative IXY divided by IX minus IY over 2. And so this gives us an equation. So we take our current IXY, our current IX, and our current IY, and we can calculate a theta p, which is the angle from our x-axis to the nearest principal, the nearest max or min. I'll show you some example problems that show that to you. Another way to get this formula is at the principal values, the IXY at those principal values at the max and the min are 0. And so if you take the IXY equation and set him equal to 0 and solve for theta, you basically get the same equation. You get tangent of 2 theta p is equal to negative IXY divided by IX minus IY over 2. So this gets us the same equation. So given an IX, an IY, and an IXY, I can solve for theta p. Once I get theta p, I can plug that back into my transformation equation, and that will give me the I at that angle. And then if I take that theta p plus or minus 90, that will give me the I at 90 degrees from that, which is the other one. So those are my transformation equations. The summary of those transformation equations is in your file. And that summary, I'm sorry, it's in your folder. It's on the OneDrive. It's also on the website. So these are the theta equations. These are the 2 theta equations. This is the I max or I min equation, which we'll talk about later. And this is the tangent 2 theta p equation used to find theta p. And again, theta p is the angle from the x-axis to your nearest I max or I min, which is called a principal I. I know I threw it a lot at you here, but this derivation shows us where IXY comes from, because IXY just showed up in the derivation, and we need IXY to coupled with IX and IY to calculate these I's at the various orientations, and ultimately to get our Imax and our Imin, which are kind of important. Also, we're going to take these two theta forms of these transformation equations, and we're going to use those to obtain our Mohr circle, which is another tool or technique we can use to find Imax and Imin and to find I values at different orientations. So we'll go back over this again and again over the next few lectures. But again, we've bit the bullet, we've taken the plunge, we did the derivation, and so now we can build on this and so that you can understand it better.